Which of the indicated hydrogen atoms is most acidic? So in order to determine acidity, we want to look at the stability of the conjugate base, right? Because if we think about an acid, HA dissociates into A minus plus H plus. The more stable this guy is, the more of it that's going to exist at equilibrium, right? The less able that this is able to go back. Here it's not going to want to pick up an H if it's really stable, right? So that's the idea. It's just going to stay in this form if it's stable, so that this guy will donate most of its protons, and equilibrium will lie on this side. That's acidity 101, right? So we want to look at stability of the conjugate base. So let's deprotonate this guy at the various positions and see how stable it is, right? So this guy right here, we could deprotonate it there, have a base can pick up those protons. So this guy puts a minus charge there, and what we need to take note of is this is an sp3 carbon. So we can't move this electron density really away from this carbon, right? Best we could do is something like we could go here. If we go there, we'd have to see. There's really not much we can do. Actually, we could go. Let's see. If we went here, right? We go here, right? And what we'd end up with is now this, and now a minus charge here, right? But no matter how we move the resonance, we'll always have minus charge in this benzene ring, so it doesn't get, resonance doesn't pull it too far away, right? So now let's redraw this. It was like this. Here's H, this was A. So not that acidic for A. Okay, B. So this C right here, C, H, and we pluck off one of the H's, we have the conjugate base. So this guy is again sp3 carbon. So we cannot withdraw electron density to the right. We may be able to draw some to the left, right? We could go here and put some minus charge in the ring, right? And then we could move that again, put some minus charge here we got a double bond here, right? So we can move this minus charge around the ring, but all in all, it doesn't pull that minus, it pulls it to the left, not to both sides, right? So I think we'll be able to do better as we move on to this compound. So let's keep looking. Right. So messing up this ring here. Okay. Redraw it again. Like this. Okay. So that was B over here, which was a little stabilized by resonance, but not all the way. So this guy. And so you should know about these alpha carbons from the reactions you did with alpha carbons and them basically acting as bases, right? They can go like that. Or I'm sorry, them acting as alpha acids, right? So we lose this proton here. We can get a minus charge here. And so, right, we can delocalize this to the right. We can go here and up here, which would put a minus charge on that guy, double bond here, right? So resonance pulled a little electron density to the right. We can go to the left as well, right? We were right here. We can go here, here, right, and get this minus charge up here. So we withdrew electrons to both sides of the C. So right, it's like this electron density is being pulled both ways away from the C. So that's good. That's like that's a good acid, right? And we've seen it act as a efficient acid in a lot of the reactions in like chapter 17 maybe, something like that. Okay, so right, that guy's looking good. Okay, so that was that. This guy was CH2, that was C. So now let's check out D, right? Okay, C, H, loses a proton, minus charge here now. So we could pull it to the left, and we get a double bond here, we get 2 up there, minus charge on the O, right? But then this is sp3, so it can't go any further, and there's nothing to the right of it to withdraw electron density to the right. So basically C is the only one where through resonance we can show the electron density was withdrawn to both sides of the carbon atom. And what that did was it stabilized that conjugate base, right? It moved minus charge off of a carbon, which carbon's not that electronegative, you don't want minus charge on it, right? But hopefully through this long-winded explanation, you see that C is the most acidic. This guy. Okay.